Imagine dropping a solid block of steel into the ocean. It sinks almost instantly. Now imagine taking thousands of tons of that same steel, shaping it into a vessel hundreds of meters long, filling it with cargo, fuel, machinery, and people. And somehow, it floats. Some of the largest ships ever built weigh more than 500,000 tons. So how is that possible? The answer isn't magic. It's one of the most fascinating tricks of physics, and it all comes down to one simple idea. Water can push. More than 2,000 years ago, the Greek scientist Archimedes discovered that when an object enters water, it pushes some of that water out of the way, and the water pushes back. The upward force produced by the displaced water is called buoyancy. If that upward force is strong enough to balance the weight of the object floats. If it isn't, the object sinks. But there's a strange question here. Steel is much denser than water. So why doesn't a steel ship sink? The secret is that a ship isn't a solid block of steel. It's mostly empty space. Think about a steel bowl. If you throw a flat sheet of steel into a swimming pool, it sinks. But bend that same sheet into a bowl, and suddenly it can float. The amount of steel hasn't changed. The weight hasn't changed. Only the shape has changed. That shape allows the steel to enclose a huge volume of air. And now we're no longer talking about the density of steel alone. We're talking about the average density of the entire ship, including its steel, air, empty spaces, cargo, machinery, and everything else inside it. If the ship's overall average density is lower than the surrounding water, it floats. That's the basic secret behind every enormous steel ship on Earth. But knowing this principle doesn't mean building a giant ship is easy. For centuries, ships were mostly made from wood. Wood was relatively light and naturally suited to floating structures. But wooden ships had serious limitations. They could rot. They could burn. And building enormous wooden structures required extraordinary amounts of timber. Eventually, engineers began experimenting with iron and then steel. At first, the idea seemed ridiculous. Everyone knew that an iron bar sinks. So why would an entire ship made of iron behave differently? Because the ship wasn't an iron bar. It was an enormous hollow structure designed to displace a tremendous amount of water. In the 19th century, iron ships proved that the idea actually worked. One of the most famous examples was the SS Great Britain, designed by Isambard Kingdom Brunel. When it entered service in the 1840s, it was an engineering marvel. It was nearly 100 meters long and constructed largely from iron. And instead of sinking, it crossed the Atlantic. This demonstrated something important. The question wasn't whether iron or steel could float. The real question was whether engineers could design the hull correctly. And that brings us to another important part of ship design: balance. A ship doesn't simply float at one fixed level. Its position in the water depends on its weight. Add cargo, and the ship sinks deeper. Remove cargo, and it rises. Engineers call the depth of the hull below the waterline the ship's draft. But what happens when a ship isn't carrying enough cargo? This is where ballast tanks become extremely important. Large ships can pump seawater into specially designed tanks. The additional weight pushes the ship deeper into the water and can improve its stability. When a ship loads cargo, some of that ballast water can be pumped back out. This allows the crew to control the ship's weight distribution and keep it within safe operating limits.
Before we uncover the next strange chapter in history, if you enjoy fascinating stories like these, take a second to like this video and subscribe.